Hello everyone, welcome to the fourth workshop of DGSM and FunKit. In the last workshop, we discussed about the basics of sequential circuits. In this workshop, sequential circuits will be continued. First, I will quickly go through the topics covered in the last workshop. So this is the state table. State table consists of sections labeled as present state, input, next state, and output. Present state section shows the various states of the flip-flop at any given time, say t. Input state section gives a value of all possible inputs for each state. Next state section shows the states of flip-flops after one clock period, say t plus 1. Output section simply gives the output corresponding to each present state. Now the state diagram. Basically, state diagram is the graphical representation of state table. It shows all the states, possible inputs, next states, and their corresponding output. State of a flip-flop is represented by the binary numbers present inside a circle. Transition between states is indicated by the directed lines connecting the circles. The directed lines are labeled with the two binary numbers separated by a slash, where former is the input and latter is the output. This is an example of a state table. Here you can see that if my present state is 0 0 and input is 0 1, then my next state is going to be 0 0 and the corresponding output is 0. Same happens with if my present state is 0 0, input is 1, and then next state will be 0 1 and the output will be 0. Same thing is represented here in the state diagram. If you see here, this is my state 0 0, and if the input is 0, then my next state is going to the, someone is waiting in the lobby. Smriti, are you here? There is someone waiting in the lobby.
Yeah, I've admitted.
Okay. So here if you see my present state is 0 0, and if the input is 0, this is the input. If this input is 0, then my next state is going to be 0 0, and the corresponding output will be 0. If I am in state 0 0 and the input is 1, this input is 1, then my next state is going to be 0 1, and same thing happens with the 0 1. If my present state is 0 1 and the input is 0, then I am going back to the state 0 0, and output here will be 1. Similarly, if I am in state say 1 0, and if input is 1, then again I am going back to the state 1 0, and the corresponding output will be 0. And if it is input is 0, then I will be going back to the state 0 0. This is the same thing represented here in the state table, and basically state table and state diagram are just two ways of representing any information. Now the state reduction and assignment method. The state reduction method is used to reduce the number of states in a state diagram, which in turn reduces the number of flip-flops used in the circuit. The state reduction is done by removing one of two equivalent states. Two states are said to be equivalent if they have the same next state, input and output. The state assignment method is used to assign some binary value to different states so that flip-flops can store the state. We can have different methods of state assignment. Like if we have 4 different states, we can use binary encoding, gray encoding, one hot encoding, etc. For example, if you consider we have 4 states, A, B, C, and D. If we do the binary encoding, then my A state will be represented by 0 0, B will be represented by 0 1, C will be by 1 0, and D will be represented by 1 1. Now if I use the gray encoding, this is for binary. If we use gray encoding, then it will be like 0 0, then 0 1, then 1 1, and then 1 0. And if I use the one hot encoding, Basically, one hot encoding requires more number of flip-flops. This is one hot. It will be like 0 0 0 1 0 0 1 0 and then 0 1 0 0 and 1 0 0. So basically we have different ways of doing state assignment. All depends on the type of circuits we are implementing. Now this is an example to illustrate the state reduction and assignment method. As I mentioned earlier, two states are equivalent if their next state and output are same. So here uh, if you see the present state, if my present state is 0 and input is 0, then my next state is going to A, and if the input is 1, then next state is going to F, and the corresponding output is 0 and 1. If you see carefully, this state E and G are equivalent because E also has the same thing AF and 0 1. So we can see clearly these E and G are equivalent. Similarly, if we remove this G, and G will be replaced by E. So now if you see D and F are the equivalent state because D also has E and F as next state and output as 0 1, and also F has E and F as next state and 0 1 as the output. So this F state is also removed from the state diagram. So here you can see this is the reduced state diagram of this circuit, and here this is the reduced state table. You can see here also there is no F and G state. Now this is the procedure to design any closed sequential circuits. First we create a description on the basis of behavior of the circuit, then we obtain the state table using the above information. Then the number of states can be reduced by state reduction method. Then we do the state assignment. Then we determine the number of flip-flops required, and also we assign a letter symbol to each. Then we choose the type of flip-flop to be used. Basically we can use any type of flip-flop, but generally we prefer to use D flip-flop because it is easier to implement. Then we derive the circuit excitation and output tables from the state table, and then we obtain the expression for output and the flip-flop input. Then we finally implement the circuit. Is it clear till this point? Is it clear? Yes, okay. Now this is an example to understand the design procedure of a sequential circuit. Uh, we have simple state diagram, and for that we draw a we have simple state diagram, and for that we write a state table. Again, if we see here, state is 0 0, and if the input is 0, then I will be at 0 0 state, and if the input is 1, then I will be going to a new state, that is 0 1. Same thing is represented here. If I have input 0 for 0 0 state, then the next state is going to be 0 0, and if my input is 1, then the next state is going to be 0 1 for state 0 0, and for state 1 0, if the input is 0, then I will be at the same state, and if the input is 1, then I will be going to the next state, which is 1 1. Same thing is written here. If my present state is 0 1 and input is 0, then I will be at the same state, that is 1 0, and if input is 1, then I will be going to 0 1. 1 minute, there is little mistake. Okay, yeah, this is for 0 1. For this for 1 0, if my input is 0, then I will be at 1 0, and if my input is 1, I will be at new state which is 1 1. For 1 1 state, if the input is 0, then I will be at the same state which is written here for state 1 1, and if the input is 0, I will be at the same state, and if the input is 1 at state 1 1, this machine will be going to at 0 0 state, that is here 0 0 state. Yeah, and to design this circuit we do following steps. First we write the input state table. This is written here, and then we write the excitation table of any flip flop. Here we are considering the JK flip flop. So what we do, we simply analyze the state table and the excitation table. If you see clearly here, if uh, present state is 0 0 and input is 0, then we will require two JK flip flop whose now I am considering two JK flip flop. One is JK and another one is say this is AB. So it will have JA and KA input. So my JA will be 0 and KA will be don't care. So that next state will be 0 0, and if it is 0 0 and input is 1, then next state is going to 0 1, and for that we require two flip flop the JK flip flop input to be 0 comma don't care and 1 comma don't care. Means yeah, I think that is sufficient. Here what we do, we simply create a k map to get the JK and J and K value on the basis of inputs. So this is represented here, and this is the required circuit that we are drawing. Now the Mealy and Moore machine. Basically, in Mealy model of sequential circuits, output are the function of both present state and inputs, whereas in Moore model, outputs are the function of present state only. In Moore model, the outputs of the clock are synchronized with the clock, whereas that's not always the case for a Mealy model. This is an example of state diagram of a Mealy machine. The inputs and outputs corresponding to state transition are written over the directed lines, and the inputs and outputs are separated by a slash. So this is the main difference, that for a Mealy machine you get the output written just behind the input. This is the output and this is the input. This is an example of a modem state machine. In this, the outputs are written inside the circles. Here, that is missing. We can consider that if we write here, we can consider that the output are 0 for this. We can consider output for this state is 0, for this as 1 and 0 and 0. So this is the difference. Like in the Moore model, we only write input over the directed lines, and outputs are written inside the circle. Can anyone tell me what will be the difference between the circuit of Mealy and Moore model? Hello. Can anyone tell me what will be the difference between the circuit of Mealy and Moore machine? Anyone? At least say yes or no. Sandeepan, are you there? Okay, I will tell it later. Now the sequence detector. Basically, sequence detector is a sequential state machine that can find the occurrence of a particular bit stream from a string of bits. It produces output as 1 if that particular sequence is detected, otherwise the output will be 0. The sequence detector itself can be classified as overlapping sequence detector and non-overlapping sequence detector. For overlapping case, the end of a detected sequence can be the starting of next sequence, and for non-overlapping case, this cannot be considered. If you see, this is the method, this is the procedure to design a sequence detector. Here you can see, if you consider this as an input, we are going to detect 101. So if you consider this input, uh, we are drawing here is state diagram. For a state diagram, if you see, it requires three different states, A, B, and C. Here we are considering for non-overlapping case. Now, if you see, if my input is 0, that is represented here, this is not part of my string, that is 101. So I will be at the same state. If I got the 1 as input, that is here 1, so the input, this one can be the part of our sequence 101. So we simply move to the next state. Now we have detected 1 and now we require 0. So if I got 1 as the next input, this is not our sequence and it can be in the start of next sequence 101. So I will be at the same at the same state. So again I will have I have only detected 1. So again I require 0. If my input is 0, that is 10, then this is the part of our this is the part of our sequence which is we are going to detect. So we simply move to the next state, and if 1 again happens, then this is my the detected sequence, and here I will produce output 1 and pass to the again reset state. This is for the case of a non-overlapping sequence detector. Now if I consider the 1 minute, I am getting a call. If I consider for overlapping case, what we do, we simply make another state diagram for the non-overlapping case. If my initially I will be at the reset position, and if the input is 0, then I will be at the same state, and if input is 1, then this can be the part of our sequence 101. So I will simply move to the next state. I have detected 1, and if I get the 0, so I will simply move to the next state. Otherwise I will be, if I get 1, then that one may be the part of next sequence 101. So I will be at the same state. Now here I have detected 1 and 0. If I get the 1, if I get 1, then my sequence is detected. So output will be 1, but this one can be the start of sequence of uh, next sequence 101, like it can be like 1001. So in this case we will get output as 11 because there is 2 times 101 repeating one, this is, and another one is this, means we are getting 101 repeated 2 times. So what I am trying to say here is, if I am at this state, I have detected 10, and next when 1 occurs, this one can be start of next state. So I will simply move to the state 10. I think there is some mistake here in this picture, but you will correct it. this will be like this, and here yeah, this will be not here. Okay, is it clear?
Yes, bhai.
Okay, did you got why I said this is wrong? This path is wrong.
Yes.
Okay, now this is the design method to design that sequence detector. What we do, we simply write the state table for the given state diagram, and then we implement it using it can be implemented using any flip flop, but generally we use D flip flop because it is easier to implement. So here this state table is simply what I sort the state diagram. Here if you see for 0 0 and input 0, next state is going to be 0 0, and same thing is repeated. And what we do now, now we simply write a kmap for the like this is implemented in this way. Basically we have two D flip flop x and y, and its input are dx and dy, and these are maintaining like this is qy and this is qx. So qx and qy will be my two states, like two bits of state, and it will be its value can lie between 0 0 0 1 and 1 0, that are my area of interest for the state diagram. So here you can see if my present state is 0 0, input as 0, then next state is going to be 0 0, and to get 0 0 as output of D flip flop, we have to apply 0 0 to its x and y input. So here you can see this is the K map. It has two inputs x and y. X and y are basically qx and qy. And if my input is I, so here I have drawn the K map. Okay, now considering the change of state case, like this dx is equal to 1. This dx is 1 for 0 0 and 1, which is written here 0 0 and 1, and again dx is 1 for 101, that is here. So if I draw the K map, I will be circling this like this way, and that I will get dx is equal to y complement I. Y complement means it is the qy complement with ending with I. And similarly, if I see the dy input is 1 here, and for that the present state and input are 100. So this is 100, and here we have taken this don't care condition for simplicity. So my dy will be what it will be, end of qx and I, means qx and I bar. This will be my dy. Similarly for the z, z where y I, one minute, this should not be z, this should be okay. Output, here you can see that output z, this is output z. This is one for only one case for which y and input I is 1, so it is simply the end of y and input. So z is my y and I. Okay, if you get from the previous equation, my output z was y and I, that is written here, and dx was y bar I. dx was qy bar and I. So this is the dx is the end of input I, and the qy, or here it is y bar, so it is the end with I and y bar. and then that is passing to that is passed to the dx. Similarly, if you see from the previous slide, dy is the xi complement. So here you can see dy is the uh, ending of x with I complement, and this x comes from y output of the d flip flop, second flip flop, y flip flop. Can anyone tell me here, is this mealy machine or Murray machine? Anyone? बोलो कोई. Is this mealy machine or Murray machine? Hello, बोलो कोई. Is this mealy machine or Murray machine? Sai Harsha, are you there? If you are not getting, you can simply say, I don't know.
Yes, by I'm there. I'm
What is
not
this?
getting.
Okay. Uh, Remember what I told. For the mealy machine, output, say output z is the function of, uh, for the mealy machine it is the function of states of the flip flop, like q, x, or here it is x and y, and along with the inputs. This is for mealy machine, and while for the Murray machine, z is the function of only states of the present state of the flip flop, like it is the function of only x and y. Now can you tell me, is this a mealy machine or Murray machine? See here, z is the function of,
Melee machine.
yes, z is the function of y and I, so it is mealy machine.
Yeah, why X is connected to Y
What?
in the second D flip flop?
Oh, sorry. This x should be here, like it should be like. If you are not getting any point, then you can simply tell me. So this x should be connected to the AND gate. By mistake I connected y with the x input. That's my mistake. Is it clear now, or should I repeat last this procedure once again? Anyone can tell me?
No, bhaiya, you can continue.
Okay. So this is homework for you. You have to design 101 sequence detector for the overlapping case, and then I will be floating an assignment, and this will be the part of that assignment. Now the counters
Hello,
and
Bhaiya.
register. Ha, yes.
There is a doubt in chat there. Can you look at it
Okay,
once?
1 minute. Can you explain the diagram? That circuit diagram for 101. You can write on this chat box. Circuit diagram for 101 overlapping sequence detector. You can write on the chat box. I am waiting. Okay, previous ones means This diagram. This diagram.
Your screen is frozen by, I think.
Okay. Is it visible?
Yes, Bhaiya.
Okay. So you have doubt in this diagram. Sandeepan, you can see the chat box and then tell me. Or Sai, you can also do the same.
Yes, Bhaiya, I guess that one.
This diagram. Okay. So
नहीं
here
नहीं
what we.
एक मिनट भैया वो नहीं था मतलब
अच्छा ठीक है प्रीवियस वन ओ भैया कौन सा है एग्जैक्टली बताओ तो ये वाला
you can specify the diagram in chat, then it will be clear. Right? Whoever is asking in the chat.
Harshita, you can write the page number on this chat box, page number of the PPT, or you can at least explain which
I'm
diagram you are.
audible.
Yes, you are audible.
Bhaiya, the one you explained just before.
For the circuit of the 101 overlapping detector or the this table, state table and the came
After that, I
after the table. Acha, this circuit.
not able to see your screen.
1 minute. This circuit.
Yes.
Okay. If you see last diagram, I got this expression dx is equal to y complement I, dy is equal to x I complement, and z is equal to end of y and I. This is the same thing. Z is the end of y and I, and dx, this dx input of the flip flop, this dx input is the end of y bar and I. Y bar is nothing but the output of the second flip flop, complement of the output of second flip flop. And if you see again last slide, dy was the x and I complement. So here dy is the end of x and I complement, and this x is the output of flip flop x. Then I told that this is an example of mealy machine. Why? Because in mealy machine we have output z, which is the function of state present states of the flip flops and inputs. So this here, if you see, output is y and I, means it is dependent on the input. So this is mealy machine, and if it was Moore machine, then my output z was taken from here or here, or some logic like and with y and x. That was the case for a Moore machine that I asked earlier, that what will be the difference between mealy machine and the circuit in the circuit point of view. That's the here, that for mealy machine output, this input will contribute to the output directly, but for the Moore machine this input will not contribute to the output directly. Is it clear now?
Yes, Bhaiya. Thank you.
Welcome. Now the counters and the registers. We will be seeing about ripple counters, synchronous counter, and a few other counters. Then we will see registers, see shift registers, then universal shift registers. Basically, the counter is a special register that goes through the sequence of prescribed states on the application of clock signal. The counters can be further divided into two categories. One is the asynchronous counters, and another one is the synchronous counter. The asynchronous counter is also called the ripple counter. In ripple counters, the output of few flip-flop goes to the clock input of some other flip-flop. While in the synchronous counter, there is a common clock signal for all type of the flip-flops. So here And this is the circuit of the BCD ripple counter. A BCD counter is a counter that counts from 0 to 9. Here you can clearly see that output of each flip-flop is fed to the clock input of next higher order flip-flop. Uh, Here, if you see clearly, here this output A0 is fed to the clock input of next order flip-flop. Here also it is fed to the next flip-flop. Here it is not fed. Okay, so we can design BCD counter using different type of flip-flop. Here it is designed using T flip-flop. Here it is designed using D flip-flop. So here main thing is that it is asynchronous. Why? Because here the A0 is getting into C of the next flip-flop and so on. So that is the main difference between synchronous counter and asynchronous counter. If you see carefully, it has the single count output input. That count out input is the clock. Like here I will apply clock signal. Also we have two type of binary counters. One is the binary up counter that counts from 0 to 9 in this sequence, and another one is the down counter that counts from opposite, like 111 to 011. This is the BCD down counter. Now this is the circuit diagram of the mod 6 ripple counter. Mod 6 means it count up to 5, and as soon as the output goes to 6, the output of the NAND gate. If you see here, when output goes to 6, 6 means 1 1 0 1. If output goes 1 0 0, then the output of this AND gate will be 1, and this one will reset all the flip-flop, because here you can see there is bubble at the clear input. This bubble means that when clear input is 1, means it is high, then it will be going to reset, clear it. So as soon as my 0 0, as soon as this, 1 minute, it should be like this way. 1 1 0, 1 1 0 means we are counting from 3 to 1. So 1 1 0 means 6, and if 6 arrives at the state of the 3 flip flop, then my output 1 1 will create output of the NAND gate as 0, and then it will be clearing all the flip flops. Like here I yeah, it will, if it is 0 here, here also it is 0, then it will be going to clear all the flip flop. Same thing is written here. Here it is written that clear and bar on it. Bar on it means clear is the active low. Active low means when the that input is low, my output will be going to change accordingly. So here my input is 0 for the clear. 0 for clear means it will be uh, cleared, means 0 0 0 will be next output. So as soon as I reach this point, this point means after 101, when I reach 100 110, then it will be immediately going to the 0 0, means my count will be repeated infinite from like 0 to 5, and then 6 will be not there because this is asynchronous one. Now the synchronous counters. As I mentioned earlier, synchronous counters are synchronized with the clock signal. So a single clock signal is used for all the flip flop. So here this is the state diagram of the 3-bit binary counter. Here you can see the last bit of counter is changing each time. Like this is the state diagram 0 0 0 0 1 0 1 0. So this is counting from 0 0 0 to 1 1 1. Like it is counting 3 bits. If you see carefully, here my last bit is going to change after each clock cycle. So I can use a T flip flop, which is here, T flip flop, and that input T0 will be 1. Why? Because for input 1 my output will toggle every time. Now if you see for the second bit, it is simply toggled if first bit is 1. Here if you see, uh, here this is the first bit is 1, then in the next cycle it is toggled, and here if you see it is 0, first bit is becoming 0, then this one will not be toggled, and here again if you see the first bit is 1, then it will be toggled, the second bit will be toggled, and here also if you see clearly first bit is 0, then second bit will not be toggled, that is here, and here also if you see my first bit is 1, then the second bit is going to be toggled, which means that this input ta1, this ta1 can be simply a naught, that is what written here, this a naught, this a naught is simply going to the t1 input of the second flip flop, t flip flop. For the third bit, it is toggled if other two bits are 1 and 1. So here if you again see here, if you see my two bits are 1 1, then my first bit is going to be toggled, like here it is toggled to 1, and here also my first two bits are 1 1, then this is going to be toggled. So what we do, we simply take input of third flip flop ta2 as a1 and with a0, which is what written here, this ta2 is the and with a1 and a0. Is it clear? This is the way to design any counter. Is it clear?
Yes, Bhaiya.
Okay, can we use another flip flop for this? Anyone can tell me? Can we use another flip flop for this? बोलो कोई. Okay, now the ring counter. A ring counter is a special counter which counts the one hot code. Like if it is 4-bit ring counter, then it will be count like 100, 0100, 0010, and then 001, and this will be repeated. It is the special type of shift register that we will see in further slides. So here you can see this is the circuit of the 4-bit ring counter. The design is simple, that you have to connect all the 4 D flip flop in series, and the output of fourth flip flop goes to the input of first flip flop. If you see carefully, all these 4 flip flops are connected in series, and the output of last flip flop is going to be input to the first flip flop. So we will get this kind of pattern, 100, like here it will be 1 1 0 0 0, then next this 0 will pass to this input. So next it will be 0, and this 1 will be passed to the second, so it will be 1, this 0 will be passed to the second 0, and this 0 will be passed to next flip flop. So again I will get this 0 0 1 0, and then after I will get 0 0 0 1, and after that this one will again goes to the first flip flop, so I will get 1 0 0 0. So this is the special property of ring counter, like it is generating one hot encoding. Now this is the Johnson counter. The Johnson counter is almost similar to the ring counter. but there is slight difference, and that difference is that the complemented output of last flip-flop goes to the input of first flip-flop. Here you can see all these three flip-flops are connected in series, and then all the four flip-flops are connected in series, and the complemented output of fourth flip-flop is going to the input of first flip-flop. So if you consider four like initial condition as 0 0 0 0, then next state will be like here it will be 1. So my next state will be 1 0 0 0, and then again it will be like 1 1 0 0, then it will be like 1 1 1 0, and then again it will be like 1 1 1 1, and then again it will be like 0 1 1 1, and so on. This will be repeated. Here you can see the same thing. Initially my four states were 0 0 0, and then I will be getting 1 0 0, and so on. So if you compare it with the ring counter, n bit ring counter have n states, n states, while for this Johnson counter we are getting 2n states for n number of flip-flop. If you count the number of states here, there are total 8 states, and for the 8th state we are using 4 flip-flops. So 2 into n, that is 4, 8 state. And if you see previous thing, we are getting only 4 different output, like 1 0 0 0 and 0 1 0 0, and here 0 0 1 0, and here 0 0 0 1. So here we are using 4 flip-flops, and we are also getting 4 different states. Now the registers. The registers are a group of n flip-flops that are capable of storing n-bit binary information. The simplest register is a group of flip-flops without any gates. This is the circuit diagram of a 4-bit register. It has 4 inputs, I0, I1, I2 and I3, through which the data is fed to the register, and it has 4 outputs, A0, A1, A2 and A3, through which the register value get outputted. Now the register with parallel load. Loading means the transfer of new data into the register, and the parallel loading means that all the input data bits are get loaded at the same clock edge of the clock. We can have two different methods for the loading any new data to the register. One way is to control the clock signal via gate, but this creates uneven propagation delay. Another way is to control the D inputs of the flip-flop. That will be cleared in the next diagram. Here if you see my load input, if my load input is 0, then here it will be 1, and here it will be 1, and here it will be 0. So 0, then the output of this AND gate will be 0, and here the input to the this D flop will be AND of A0, and 1 means A0 means A0. So here what will happen, my output is going to be simply the previous state. So when load is equal to 0, only the last data will be registered, while any new data will not be registered inside the register. But if we consider load is equal to 1, if we consider this load as 1, then this will be 0, and this will be 1. So here 1, and this 0 will create 0 here, and then 0 here. So what is going to happen, this D input is connected like this. The output of this AND gate will be AND of I0 with 1. So it will be here it was 1, and here it is I0. So my output here is I0, and input to this D flip-flop is I0. So it is here like 4-bit normal register with parallel load. So this is the circuit of 4-bit register with a load control input. Is it clear? Okay.
Yes, sir.
Okay. Now the shift registers. Shift registers are a special register that are capable of shifting its binary information in one or both direction. That direction can be anything like left shift or right shift. This is the circuit diagram of the shift register. If you consider, here we are getting input as say 100 serial input, then this 0 will be input to this flip flop, and in the next clock cycle it will be here, and in the next clock cycle this will be 0, and so on. So basically what is happening here, any data inside this flip flop is going to the next flip flop. This is called the right shift. Similarly, we can have left shift, that will be just opposite of this right shift. Okay, now the universal shift register. We have different type of registers. One is the unidirectional shift register that are capable of shifting in only one direction. It will shift either in right direction or left direction. And we can have bidirectional shift register. It is capable of shifting in both direction. And then we have the universal shift register. It has both shifts and parallel load capabilities. So we can use at both type of register. One is the shift register and another one is the parallel load uh, register. The most general shift register has following capabilities: a clear control to clear the register to 0. Also it will have a clock input to synchronize the operations. Also it will have shift right control to enable the shift right operation, and the serial input and output lines. If you go to the last slide, for the serial input we have serial output. So shift register will always take serial input and produce serial outputs. So if you consider this third point, shift right control to enable the shift right operation and the serial input and output lines. Same thing will happen with the shift left. Shift left control to enable the shift left operation and the serial input and output lines. Also it will have a parallel load control to enable the parallel transfer of n input lines associated with the parallel transfer. Also it will have n parallel output lines. Also it will have a control state that leaves the information in the register unchanged in the presence of the clock. Now this is the circuit diagram of a 4-bit universal shift register. If you see, we have two different bits for the control lines. One is S1 and another one is S0. So we are designing in such a way that if the control signal is 00, then register will not change anything, means it will remember its old state, like it is memory state. If its input is 0 1, then it will shift right, and if it is 1 0, it will shift left, and if it is 1 1, then parallel load. If you consider this diagram, if you see for the 0 0 case, like for the input to the this mux and all the four mux, if this s1 and s0 are 0 0, then this will be the path for each output. Here also if you see, what is happening here, the output of the D flip flop is going to the input of same D flip flop. So what will happen, it will simply remember its old state, means it will not change any value on application of different inputs. And if you consider the case of 0 1 input, then 0 1, see here, it will be If you see carefully, this is the circuit diagram of the shift right register that I explained earlier. For the 1 0 case, for the 1 0 case, see here, for the 1 0 case, this is the input serial input for shift left operation. And if you remember the I told that universal left shift register is the just opposite of the right shift register, so it will be just opposite, like this A0 will be going to the input of all other flip flop, and here A1 will be going to the, so this is an example of the shift left register. Now if you consider the last case, that is 1 1, so when my S1 and S0 are 1 1, so this will be the path to the flip flops. Here you can clearly see it is simply the 4-bit parallel register. So this is the working of the 4-bit universal shift register. Okay, that's all from my side. If you have any doubt, you can contact any one of our coordinators. Any doubt?